In this example, we want to find all solutions to the equation 4 sine squared of theta minus 3 equals 0. To do this, we want to first isolate the trigonometric function term, and then use what we know about trig functions and their special values to try to find out the actual values of theta to make this work. So I can rewrite this equation here as 4 sine squared of theta equals 3. Dividing by 4 gives me sine squared of theta equals 3/4. Taking a square root of both sides gives me that then sine of theta must equal plus or minus square root of 3/4, which is the same thing as plus or minus square root of 3 over 2. Now we know what values of theta solve this equation, right? Sine of theta being positive root 3 over 2 gives me values like theta is pi over 3 and theta is 2 pi over 3. Those both have that coordinate in the positive y direction. Similarly, for sine of theta is negative root 3 over 2, we also get two solutions, and we get those at 4 pi over 3 and 5 pi over 3. Those are now negative in the y coordinate, but they still have the magnitude value of root 3 over 2, and these are all the angles with reference value pi over 3, which ties them all together. But these are not all the solutions. They are all the solutions on one round around the circle. How do I get all of my solutions? Well, I take each of these, and I get a new one every 2 pi I add to it. So all the solutions I get here are pi over 3 plus 2n pi, 2 pi over 3 plus 2n pi, 4 pi over 3 plus 2n pi, and 5 pi over 3 plus 2n pi for n any integer. So I get 4 solutions on each loop around the circle, and if I do more loops, I just get 4 solutions every time around, so I will get 4 solutions, all separated here by 2n pi each time. That's how you set up and solve this trig equation to get all solutions, not just those on a certain interval. You can find all solutions with a method like this here.